Hey everyone, so we're going to talk about vector math and introduce some vector math in this video. This is going to be a quick video, and I'm going to be reviewing some things that you already know and then also introducing some things that you might not yet know. So we'll talk about the difference between scalars and vectors. We'll talk about vector components and talk about vector notation. We'll talk about adding vectors and then multiplying vectors by scalars, and we'll talk about I hat, j hat, k hat notation, which is probably going to be new to you, and we're going to use it a lot. So it's something to get familiar with right away. So this is all in preparation for your first assignment, which is going to be on vector math, and so we're going to use this a lot. It's going to come up over and over and over again, so it's good to get this stuff down right away. Okay, so what's the difference between scalars and vectors really quickly? So scalar quantities are those that have like a magnitude, but they have no direction. So examples would be like length. The length of this ruler that I have here on my desk is 12 inches, right? And it doesn't have any kind of direction to it. It's just 12 inches. Temperature would be another example. Pressure, mass, you never hear anybody say, this thing has a mass of 12 kilograms north. Right? That just doesn't make any sense because mass is a scalar quantity. Okay, so the amount of money in your bank account would be another example of a scalar. It doesn't have a direction to it. Vectors, by contrast, have both a magnitude and a direction. So some examples would be like displacement and velocity and force and momentum. So displacement, for example, if I were to give you the displacement vector between where I am and my home, I wouldn't just tell you 10 miles, I would say 10 miles north, right? Specifying both a magnitude and a direction. Okay, that's because displacement is a vector quantity, so you need both in order to fully specify a displacement vector. Velocity would be another example. So, your average velocity driving out from Wisconsin to South Dakota might be, 65 miles per hour west. You need to specify both a magnitude and a direction. So often, but not always, we'll use this particular notation with an arrow over the top to represent some quantity that is a vector quantity, one that has both magnitude and direction to it. Just want to point out that some scalars are just the magnitude of other vector quantities, so some, but not all. So for example, speed is a scalar. It's just the length of the velocity vector, or in other words, it's the magnitude of the velocity vector. So we use the words magnitude of vector and the length of a vector interchangeably. So speed is the length of a velocity vector. So here's an example. We have a car here that goes around a curve, and the velocity vector of the car is shown at these various points as it's moving along its path. So here you can see, right, the car in the figure, it has to go around this curve. So the velocity vector has to change as it travels, right? Velocity is a vector. It has magnitude and direction. The direction of this vector must change in order for the car to swerve and follow the path. Okay. However, it's possible, for the car to maintain a constant speed while it's moving around the curve, right? So it could be that the person decides to go around the curve without changing their speed at all. Okay, so that the magnitude of this velocity vector stays exactly the same as it goes around the curve, and only its direction changes. In that case, the speed would be constant, but the velocity would be changing because the direction does change. So that's a distinction, right, between the speed, this scalar quantity, and velocity, the vector quantity. Okay, let's say that we have some vector v. It could be a displacement vector, or it could be a velocity vector, or something like that. And it points up at an angle of 30 degrees to the north of the east axis. Okay, so we'll say that the x-axis is east, and then y-axis is north. We can represent the vector by this arrow here because arrows have a magnitude and a direction just like vectors do, so we often represent vector quantities as arrows. Okay, we could say that v has a certain magnitude and it points out at this angle of 30 degrees from the x-axis. Or we could break the vector into two different components, an east component and a north component, and we could describe the vector that way as well. So this figure shows v in terms of its two components. There's the component vx pointing along the x-axis, and there's the component vy, which is pointing along the y-axis. So you can break v up into two separate components here. And then you can determine the components using trigonometry. So you have this angle here, theta. You can construct a triangle from these components, right? You can imagine if Vy is the length, say, of this side here, and Vx is the length of this side here, then you have a triangle where the hypotenuse is the length of this vector v right over here. Okay, so how exactly would you get the components using trigonometry? Well, that's on the next slide. So here we have the components drawn up as a triangle. You all are familiar with SOHCAHTOA, right? You know how trigonometry works. So sine is opposite over hypotenuse. So if we take v, this v to be the length of this triangle here, or this side of the triangle, the hypotenuse of the triangle here, then sine is opposite over hypotenuse. So opposite side of theta, hypotenuse, sine theta is going to be vy over v. And cosine of theta is going to be vx, the adjacent side to theta, over v. And so on for tangent of theta. Okay. And how would you get the hypotenuse of the triangle? Well, you know the Pythagorean theorem, right? The hypotenuse of the triangle, v, is going to be v squared is equal to vx squared plus vy squared. So let's just talk about what v without an arrow over the top means. So we use for the magnitude of the vector v, we use this operator here. So we'll write v in terms of absolute value bars around it. Sometimes you'll see it written with 2 bars on either side. But this symbol here means take the length of the vector v, or in other words, find the magnitude of the vector v. And that's going to be given by, right, just the square root of vx squared plus vy squared. So the sum of each of the components squared. And so this is, this just follows from the Pythagorean theorem, of course. We often use the shorthand notation then that v without an arrow over the top is just the length of the vector v with the arrow on it. Okay, so v is shorthand for the magnitude of the vector v. So that's always the case. This could have been vector a with an arrow over it, and then a without an arrow over the top of it would represent the length of vector a. Okay, so a lot of times you'll be trying to find, say, the components of certain vectors, and you might know that some vector has a length of 5 meters per second, and it's at an angle of 30 degrees, and you want to pick out, say, the x and y components. Well, how do you do that? Well, you just multiply. Say you want to get vx here. You can multiply the hypotenuse, so the magnitude of the velocity vector, say, times the cosine of the angle, 30 degrees in this case. And that would give you vx, right? So that's just multiplying both sides of this equation here by v. So, you know how to do trigonometry, so that shouldn't be too difficult. Notice that something that's important is that whenever you do trigonometry to figure out the components of vectors, the original vector is always the hypotenuse of the triangle. Okay, so that's really important. The vector, the original vector that you're given, that's going to be the hypotenuse of the triangle. The components are always smaller than the vector itself. Okay, so keep that in mind. Okay, let's talk about adding vectors together. So adding vectors in one dimension is not that difficult. By the way, a resultant vector is the result of summing together vector quantities. So when you add together vectors, you get out a resultant vector. Okay. Oh, and by the way, I would also like to point out, you can never add vector and scalar quantities together. Okay, that never makes sense to do that. You always add vectors to vectors, and you add scalars to scalars. You can multiply vectors by scalars, which we'll talk about in a minute, but you can't add a vector and a scalar together. Okay, anyway, the resultant, say, if you have 2 displacement vectors, one that goes 8 kilometers east, and another that goes 6 kilometers east, say that you're traveling some direction, or you're traveling east to some final destination. You travel 8 kilometers on the first hour and 6 kilometers on the second hour. Then the resultant would be the sum of those two. In the case of one dimension, it's not that difficult, right? You just add 8 kilometers to 6 kilometers, and you get out you traveled a resultant of 14 kilometers east. So notice that this is a good vector. I'm fully specifying the vector here by telling you both the magnitude, 14 kilometers, and the direction, east. And now let's say you have a case where you travel 8 kilometers in the first hour, and then you travel 6 kilometers back in the other direction during the second hour. Your resultant vector in this case is going to be 8 kilometers minus 6 kilometers because you're traveling in the opposite direction. So your resultant is 2 kilometers then to the east. So when adding vectors together in one dimension, you just need to be really careful about the sign and make sure that the sign of this when you add these two vectors together is going to be negative, since the vector is pointing in the opposite direction. Okay, so you would specify, say, east as being the positive direction, and since the second vector here is pointing to the west, that's going to be in the negative east direction. So this would be a minus 6 kilometers to the east. So when you add them together, what you get out is 8 minus 6 kilometers, or 2 kilometers to the east. Okay, adding vectors in 2 dimensions is a little more interesting. So let's say that you have a displacement vector that goes 10 kilometers to the east, and then another displacement vector going 5 kilometers to the north. Okay, so D2 is 5 kilometers to the north. What you want to do to get out the resultant, adding D1 and D2 together, is to take a vector that goes from the from the tail of the first vector to the tip of the second vector. Okay, so this is called a tip-to-tail method. Okay. Your resultant displacement here would be the vector that goes from here, the original starting point, out 10 kilometers in this direction, and then up 5 kilometers in the y direction. So notice that it really doesn't matter if you take D1 plus D2, or so if I instead reverse the order and take D2 plus D1, right, I end up with the same resultant, right? This my resultant vector points from the origin out to this exact same location. So the order of adding the two vectors together does not matter. Okay. Since I end up with something that has the exact same magnitude and the exact same direction, I have the exact same vector, because those are the two things that completely specify a given vector. Okay, so let's add some vectors together in 2 dimensions that are not at right angles now. So let's take V1, this vector pointing here, and add it to V2, this vector that points up at an angle here. Well, in order to do that, you're going to use this exact same process of taking the two vectors, lining them up tip to tail, and then starting from the tail of the first vector and extending out to the tip of the second vector. Okay, so notice these vectors here. I can take them and I can slide them however I want. I mean, what specifies a vector is its magnitude and its direction, not its location. So I can pick up this vector here, V2, and I can pick it up and slide it onto the nose of V1, and that's perfectly fine. So V1 goes out to here, and then V2 has its tip placed at its tail placed at the tip of V1. So it extends up in this location here. So my resultant vector then would point from the tail of V1 up to the tip of V2. This is my resultant vector. VR is equal to V1 plus V2. So if you draw it up like a parallelogram, it looks kind of like this. I mean, use the tip-to-tail method in order to add these things together. But you can just note that, like, if you were to pick out a side that's parallel to V2, it would look like this. And if you were to pick out a side that's parallel to V1, it would look like this. And you would have a resultant vector that's like extending across this parallelogram thing here. So this is just kind of an interesting quirk of the geometry. This is not the right way to do it. So here, this is wrong. Here, somebody is trying to extend from the tip to the tip of the two vectors. they've lined up the two tails together and then went from the tip to the tip. That is incorrect, and I have seen students do this on tests and stuff, so don't do this, right? You want to line up V2's tail at the tip of V1, and then go from the tail of the first vector to the tip of the final vector. Okay. And you do the exact same thing in the case of adding 3 or more vectors. So here I have v1 plus v2 plus v3. If I want to add the 3 together and get out the resultant vector, what I'm going to do is take v1, put it in place, take v2 then, pick it up and slide it so that its tail is at the tip of v1, so it extends down. Then take the third one, right, take its tail and put it onto the tip of v2, and it'll extend in this direction here. And my resultant is going to go from the tail of the first vector out to the tip of the last vector. Okay, so VR is the result of v1 plus v2 plus v3. Okay, so let's just do a quick example to check this and see if you're getting it. So here there's 2 displacement vectors given. D1 points straight up like this, D2 points down and to the right like this. I want you to just pause the video for a second, draw this up on a little sheet of paper or scribble it somewhere in the margin of your homework or something. Tell me where will D, the resultant vector point. So D is D1 plus D2. Okay, go ahead, pause this for 30 seconds and then I'll explain it. Okay, so in order to do this, you want to take D2, pick it up, and move its tail onto the tip of D1, okay, like so. And then you want to take, the resultant vector is going to be the one that extends from D1, the tail of D1 out to the tip of D2. So it will look like this. D is going to be this resultant vector that points from here out to there. So D is D1 plus D2. Okay. Let me just give you a physical scenario that explains why, say, this might be important in a physics class. So let's just think about a boat that's trying to cross a river, and the river has a current to it. So the boat is going to be traveling, say, straight across, wants to go straight across to the other shore. So the boat is traveling, say, this way relative to the water, but the water is flowing because there is a river current. So that makes that gives this velocity of the water relative to the shore. Okay, so the shore is fixed in place, the water is flowing this way. So you end up with, there's some velocity to the water with respect to the shore, meaning if you're standing on the shore, you see that the velocity, this extra velocity vector of the water flowing in this direction. Okay, well then the result of this, of these 2 different kinds of motions, these 2 different velocities, the boat traveling across the river and the water flowing downstream, is going to be the vector sum of these 2 velocity vectors. So this would be the velocity vector of the boat with respect to the shore. This is what somebody on the shore would tell you. This is the boat's velocity vector. Okay, so that was just an example to illustrate why we're talking about these things in the first place in a physics class. Okay, next, let's talk about multiplying vectors by scalars. So here I have some vector v. What would the vector 1.5 times v look like? Well, it would be pointing in the exact same direction, and its length would just be 1.5 times larger. Okay, so v2, if v2 is 1.5 times v, it's going to be pointing up like this. V3 here is defined as -2 times v. Okay, so that means you want a vector that's 2 times as long but points in the opposite direction. Okay, so that negative sign means that you have to have the vector pointing in the opposite direction. In fact, take any vector v, right? The vector -v is just that vector flipped with its direction flipped around, pointing the other direction. So this, if this is v, then -v has the same length, pointing in the opposite direction. Okay, so then what would it look like to subtract 2 vectors? Well, if you have vector v1 and vector v2 like this, and you want to find vector v2 minus v1, you can take v2 and then add negative v1. So remember, negative v1 just points in the opposite direction. So v2 minus v1, the resultant vector would be take v2, set it up so that it's pointing in this direction. Now take vector minus v1, its tail should go on the tip of vector v2, so it goes out like this, and the resultant vector then goes from the tail of the first vector to the tip of the second vector, so this would be our resultant vector v2 minus v1. So subtracting two vectors is not that much different than adding vectors. The only thing that's different is you have to flip one of them around first before you add them. Okay, getting close to the end here. Let's talk about adding vectors component by component. So let's say that you have some vector v that is the resultant of adding vector v1 and v2 together. So v1 is shown here, v2 is shown up here. Then the two vectors, each of them has components to them, right? So v1 is going to have two components, v1x and v1y. Okay, v2 similarly has v2x and v2y here. Now notice, right, it doesn't matter. The origin of this coordinate system is way over here on the side, but that's okay. That doesn't matter. Vectors don't have to start from the origin or anything like that. So it wouldn't matter at all if the origin was in a different place. The component of v1 that's along the x-axis is v1x. The component of v1 that's along the y-axis is v1y. They don't have to start from the origin or anything like that. Okay, so vector v is going to be v1 plus v2. So when I add the two things tip to tail, right, it's going to look like this. Okay, what are the components of the resultant vector v then? Well, notice this, right? This resultant vector extends from this starting point over here to this ending point. That would encompass both, so if we just look at, say, the horizontal components first, that encompasses both this distance, v1x, and this other distance, v2x here. So vx is just, v1x plus v2x, right, as it says here. Now vy is going to be, this plus v2y over here. So vy, the resultant vector's y component, is going to be the sum over the two individual vectors' y components as well. Okay. So you can add vectors by summing them component by component as well, right? So this would be the way that you would do this. If you're, instead of drawing vectors graphically, you want to express them in terms of numbers. This is how you would do that, right? And if you were to then go and draw those numbers on an XY coordinates chart, then you would see that this method of doing it is completely the same as adding them tip to tail in a graphical way. Okay, let's get to our final topic, which is I hat, j hat, k hat notation. I hat, j hat, and k hat are vectors that we use that point along the x, y, and z axis respectively. Okay, so we use these vectors, and then we express vectors in terms of these other vectors that are called unit vectors. And this turns out to be convenient notation. We're going to use this notation all the time, so it's really important that you learn it. Okay, now I'll just as a fair warning, when I was taught this, it was x hat, y hat, z hat, and so x hat was the vector that points along the x-axis instead of I hat. This is just, it's just different notation. But once in a while I slip into using my old notation, so it's just important for you to realize when I say, write something in I hat, j hat, k hat format, or x hat, y hat, z hat component or format, those are the exact same thing. X hat is the same thing as I hat, y hat is the same thing as j hat, z hat is the same thing as k hat. Okay. So I hat, j hat, and k hat point along the x, y, and z axis, and they also have a length of 1. Okay, so we call them unit vectors because they have a length of unity. Okay, so unit vectors get a hat over them instead of an arrow. Okay, they are vectors. They just get a different symbol because we reserve this hat symbol for unit vectors, vectors that have a length of 1. Okay, unit vectors, by the way, also have no units to them. So you might have a displacement vector in units of meters or something like that. So vectors can have units, but unit vectors always have no length. So it's not like their length is 1 meter, their length is just 1. Okay, now unit vectors then are useful because you can use them to construct other vectors. So for example, let's say you have a vector that extends 3 meters along the x-axis, 3 meters along the y-axis, and then 0 meters along the z-axis. So it doesn't extend out in z at all. Okay, so let's say this is my vector here. Okay, if the vector v extends out 3 meters in this direction and 3 meters in this direction, then I can write it as the sum of these two directions. So I can write it as the sum of 3 times I hat plus 3 times j hat. Okay, so if I hat points out 1 meter, points out along the direction 1, then I can go out 3 meters along that direction, and I can add on 3 meters along the j hat direction, and I end up right up here. Okay, so this would be my vector v. So we use these vectors then to write other vectors. So when I say write something in I hat, j hat, k hat notation, what I mean is write that vector as a linear combination of these 3 unit vectors. Okay, so you can kind of think of I hat, j hat, and k hat as if they're like the number 1 that has a certain direction to it. Okay, so I hat is like the number 1, but it points in a specific direction. So 3 times the number 1 pointing in this direction, plus 3 times the number 1 pointing in that direction, gives you this vector v. Okay, so now let's go back to our prior example where we were adding vectors using components, but let's put that in the context of this I hat, j hat, k hat notation. This will be the last thing that we talk about. Okay, so let's do that. Let's take this vector, stick it right there in the I hat, j hat, k hat plane. So these are 2-dimensional vectors, so the k hat component is going to be 0 in each case. So the vector v1 then is going to be v1x I hat plus v1y j hat. Okay, so that's v1. v2 is going to be v2x in the I hat direction plus v2y in the j hat direction. Okay, so that would be this here. So what then is the resultant v? Well, when you take v, it's going to have its 2 components, right, vx and vy. And we already said that vx is v1x plus v2x. Vy is v1y plus v2y, right? So the components of the resultant vector are just the sum over those individual components, okay? Therefore, we can just write that the vector v is v1x x hat plus v2x I hat plus v1y plus v2y in the j hat component. So this would be this is our vy, and this is our vx. Okay. So what's kind of nice about the I hat, j hat, k hat notation is that you can take these 2 things here and you can sum them together, and it's pretty easy to sum them together, right? This looks pretty easy, right? So that's in contrast to another way that you could write these vectors is you could give me a magnitude. You can give me a magnitude, say, of this vector v1 and an angle. Okay, that would totally specify both magnitude and direction. You could do the same thing for v2, but if v1 was, say, 5 meters at an angle of 20 degrees and v2 was 3 meters at an angle of 60 degrees, well, if I wrote it that way, it would be kind of hard and irritating to add the 2 things together, right? Because I would have to do a whole bunch of trigonometry and stuff to add them together. In contrast, if I just write it this way, as the linear combination of I hat and j hat, then adding them together is really no problem at all. So that's why this notation is very convenient. So I'm going to use this notation. This is the way that I'm going to give you vectors on tests frequently and stuff like that. So make sure you're familiar with this and you know how to use I hat and j hat along with components. Okay, so that wraps up our video. I hope that this helped you review the vector math that you did already know, things like trigonometry, and taught you some new notation that's going to be important for us throughout the rest of the quarter. Bye.